because the drain voltage is small. This is like the triode region, or this linear region. And then if you further increase the drain voltage, you are going to push down the drain side or not. This is much larger, and the drain voltage is very large. So then you will have a larger slope here. So the electron will further get accelerated because the slope means the field, right? We talk about the slope of the band in the electric field. So that means the electrons will further, once it jump over the barrier top, then it will fall down. But you know, a larger slope, it will fall down faster, right? So this is because the electric field will accelerate the electrons. This is a drift. So you know the drift velocity is proportional to the field by the mobility, and the field, you know, here is the slope. So if you have larger drain voltage and larger slope, then it gets accelerated faster. So then you have larger current. And this case is below the threshold, but you have large drain voltage. So the barrier is high. Although you have large slope here, but this barrier still is very high. So you don't have too many electrons here. So we will talk about this subthreshold. This is a subthreshold. We will talk about this in more details later today. But this is the saturation. So any questions about this diagram? So just think about the electrons as water and then jump over that barrier.
So the slope of the P region doesn't change at all by VD, or the source, or the drain voltage? As long as it only changes by the gate voltage, the slope?
Slope? So first of all, here, this barrier towards this side is determined by the gate voltage. You see here, right? It's determined by the gate voltage. And then this slope is determined by the drain voltage. This slope. But this initial barrier mostly is controlled by the gate voltage. But as we discussed here, it's also a little bit determined by the drain voltage as well. This is a second order effect. So we'll talk about that in a minute. The drain voltage ideally should not change the barrier height at the source side. Ideally. Okay. So here you can see what controls the current. So a well-controlled MOSFET should be, what matters here is the electrons that can come over this barrier. So what determines the electrons to jump over this barrier? Of course, it's barrier height, because electrons here have this kind of distribution. Many electrons here, and exponentially less electrons to the top as you increase the energy. So then this barrier, if you change the height, then the number of electrons that can be over will exponentially change. That means your current will change or not. So this barrier height, important. Second is this drain voltage. Right? Drain voltage will change the slope here. So once the electrons are over this barrier, it will be accelerated. Then depending on the slope, you will have different velocity and different currents. But if the drain voltage is too large, then this slope will not matter anymore. That is the saturation, because ideally if the drain cannot control the source barrier, then the number of electrons that can be over this barrier is limited by the gate only. then the drain voltage, once all the electrons are over the barrier, then you don't get additional electrons over. That means your current will be saturated. Even you have large drain voltage, they move very fast, but then the source of the electrons are limited. Then the current will no longer increase. That is the saturation. But in reality, okay, the saturation never happened because the drain voltage will also affect this barrier a little bit, as we showed in one of the earlier slides, this DIBL effect. Drain induced the barrier lowering. So that means the current will no longer saturate. We can look at some of the real simulation result for the barrier height for short channel transistor. So here you can see this is at a very small drain voltage, like 50 millivolts. And then when you sweep the gate voltage small to large, so initially your gate is this top curve, which you have large barrier. But when you increase the gate voltage, then you are going to gradually push down the band. Then you have the current flow, but very small because the drain voltage is small. And then the other case, the drain voltage is large. So here then you have the drain voltage pushed down a lot. Still you increase the gate voltage. You increase the gate voltage. But here you see that the barrier height here will reduce. So you have larger currents. So those are the real simulated band diagram. And if you look at the real IDVD curve of a measured MOSFET transistor in 2007, so in that case, in this case, the channel length is like 100 nanometer, which is not that long. So it's kind of short because the equations we derived, this IV equation in the previous slides, work only well for the micrometer scale device. If you scale your device down to like this 100 nanometer or even below, like today's tens of nanometer, then you will see this kind of IDVD curve. So it's similar as before, but you see that here it's not saturated anymore. So still with the drain voltage increase, you will increase a little bit drain current. And if you look at the band diagram of the saturation region, which is this one, if you look at this region, so you will have the band diagram like this. You increase the gate voltage from small to large. And also this is a linear region. Then you have band diagram like this. You sweep the gate voltage from small to large. So any questions? So here I think this band diagram is important. So you will use this band diagram to understand why this current flow like this. And gate voltage, drain voltage are two control laws for the current flow. First, you need to apply gate voltage to push down the barrier. Second, you need to apply drain voltage to get the electrons accelerated after they are over the barrier. All right, let's start a new section.